white light came here going inside the prism, then here is the long wavelength of the light, and these are the highest wavelength, and here is the infrared range, and this is the ultraviolet range. So let's discuss the atomic structure and how this excitation happens and how light is formed. So an atom is made of a nucleus, and this nucleus is formed of protons, neutrons, and other subatomic particles, and around this nucleus is the electrons, and between those electrons there are gaps. They are not really gaps. Modern physics doesn't say they are gaps, but these electrons are almost weightless. They almost have no mass, but they do have. And compared to the nucleus have all the mass. So there is a big gap. Like if this mass is filled with a real mass, so if you could fill a teaspoon just with material as dense as the matter in an atomic nucleus, it would weigh 2 billion tons. So, but it's not that massive. It's not that not having this weight, because there are spaces and the electrons are not as massive as the nucleus. So the atoms are having different types. Atoms differ from each other according to the protons and the electrons. But when there is different number of neutrons, you can find that the isotopes are formed. So the hydrogen, if it's having a different number of neutrons, it's turned from hydrogen to deuterium. And it's the same for carbon, from carbon 12, which is 6 protons, 6 neutrons, to carbon 13. These are all isotopes. Okay. So matter can be in different types of isotopes and different. So the isotopes are kinds of the same element, but it's just difference in the neutron number, not the electron and the proton number. If the electron number is less or more than the protons, here we have an ion, not an atom, and they are charged. So for each element there are radii of energy shells. In these energy shells, electrons revolve around the center, which is the nucleus. And for each energy shell, these spaces are not the same, and each radius 1 has energy 1, radius 2 has an energy 2, radius 3 has an energy 3, and so on. And it's not the same in different elements. So for energy, for electrons to be placed in a specific energy shell, the electron must have the needed energy for that electron shell or energy shell. But in some cases, electrons are excited with some sort of energy, like heat or mainly heat or other exciting factors. So in this case, the electron takes some energy from here, for example, and if it has the enough energy for it to go to the other shell, it will have this energy and go to the other shell, and then it stays there for something, it's in microseconds, and it loses this energy. It emits it in the form of something called the photons, and the photons are the energy packets which is light, and this energy will cause it to have different colors. So this means that each atom will have excitation in the stars that will tell us about the elements in that star. Okay? So let's see the Kirchhoff's laws of radiation. So it says that a solid liquid or dense gas excited to emit light will radiate at all wavelengths and thus produce a continuous spectrum. So here we have a source of light. Imagine it's a star with dense, which is dense, and this star will produce a continuous spectrum, something like white light, and goes through the telescope, and then when you put the prism here, you have the continuous spectrum. Okay, but in case it's not a white light, this continuous spectrum will not be emission, but it will be a very faint continuous spectrum in the background. The second law of Kirchhoff: a low density gas excited to emit light will do so at specific wavelength and thus produce an emission spectrum. So in this case we're dealing with a gas, and this gas will be excited, okay, and when it's excited it will get some light, and this light will go and be diffracted with the spectroscope, and we will have an emission spectrum, which is the energy that comes out of the atoms in that in that gas. So in the other case, which is the third law of Kirchhoff, if light comprising a continuous spectrum passes through a cool, low-density gas, the result will be an absorption spectrum. So this means that if the gas is cool, it can take energy and absorb it. So you will see when this light goes to the spectroscope through the telescope, you will find that there are absorption lines, because these lines are absorbed in the spectrum. So this way, having the emission lines and the absorption lines, we can tell what atoms are really, what elements are really there in a star with some computer simulations, and we will use these simulations and you will see how to use them. So So in the sun, there are some abundant elements in the sun. So you will see lots of spectrum, in lots of emission lines and lots of absorption lines. But does this mean that all these elements are abundant in the star? Nope. There are some abundant elements, like for example in the sun there's hydrogen, helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur and iron, but all these are having very, very low percentages. Okay, you can find that the percentage by mass is 0.3, 0.1, 0.02. It's very small, but when you look at the hydrogen is 91% by number of atoms and 70% of mass, and the same for helium, which is